Hey guys, welcome back to AlgoYogi. We are now doing graph series, and before we move on to our next problem, which is path with minimum effort, I really wanted to get through the graph, some of the graph concepts and some of the tools that will really help us get through this graph series smoothly. So I'm sure you heard about heaps and priority queues, then Dijkstra algorithm, DFS and BFS. So we're going to quickly cover these topics and understand, basically strengthen our understanding how these work in Python or any other language. We're just going to do the conceptual part. So let's get into it so that we can get through our graph series really quickly and smoothly. So let's start with heaps and priority queues. I'm sure you must have heard about heaps and priority queues, maybe together, maybe separately, but let me tell you that they both do the same job. They're both referring to the same data structure. Now, priority queues, as the name suggests, gives priority to some elements in comparison to the other elements in your queue. So queue could be like just a list of some values, and you are giving some priorities to some elements, so they are like right in the front, or you give them more preference. They reach the front first, and there are some elements waiting for them. Now heaps is specifically let's say min heap or max heap. They also give priority based on if it is a min heap or a max heap to its values, right? So right now I have written this heap, but it's actually not heap. It's let me just change it to like a regular array. Let's call it array or A. So now this array that you are seeing right here, let me write it a little closer. This array that you're seeing right here, now this could be simply represented into this binary tree. How? We could simply have these root calculated by basically I will be my root. This is my root, and then this root will have left child and right child since it's a binary tree. So it's gonna be 2 into I plus 1, that is my left child, and 2 into I plus 2, that is my right child. So now let's see, how did we, I'm just showing you how we converted this array into this binary tree, just for the representation in memory. When you are heapifying something or you're creating a min heap or a max heap, the computer is storing it as a list and just doing its calculation using the list, because there is nothing like this structure, unless you create one. Because if computer can do the job just using the indexes, then why not? So here let me just show you how we calculated it. So let's index our elements right here. So this is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So we have 10 elements right here. Now our root will always be present, the root of our binary tree will be present always at the 0th index. So 2 right here, that's the root. Let's take this as a 0. So now how do we calculate the right and left for when the root is 0? So let's calculate its left and right child's position or index. So we will be doing it 2 into 0. So root is 0. So left child would be 2 into 0 plus 1. That's the left child's position, which is 1. So 1 index, if you see right here, so this is the left child. This is the left child. You can see 5 is the left child. And then let's calculate the right child. It's going to be 2 into 0 plus 2. Now that will give us 2. So now you can see that 0 is present at this second index. So this is my right child for my root, which is 2. Now, and same way we can convert for 5. 5 is present at 1 index, so where it's going to be its left child and right child. So we can do the same calculation for 5. I'm just going to do one more, and then we know what we are actually trying to do. So that will be 2 into 1 plus 1 and 2 into 1 plus 2. So this will give me 3, and this will give me 2 into 1. 2 plus 2 is 4. Okay, so 5 is right here. 5's left child is 1, which is present as third index. Left child is 1, and right child is 10, which is present at fourth index. So now you can calculate the position of left child, right child, parent position, whatever you can calculate for this binary tree. So what I was really trying to show is that we can represent this array into a binary search tree. Now, how do we convert it to a heap? Well, in Python, we have a library that's called heap queue. That's the data structure, heap queue. So we will be importing heap queue, and then we can perform some operations on heap queue. And one of the operation is basically heapify. So heap queue, once you import heap queue dot heapify, and if you are sending in your array right here, and basically this should be giving you a heapified. By default it gives you a min heap. And what does min heap means? Like you'll be converting this to basically restructuring your binary tree, so that the most valued, which is basically most valued values go on the top, and then the least values are on the bottom, which it really means min heap means the minimum value should be on the top, right? So if we convert this in Python, and the same concepts can be used in other languages as well, but like we are doing it, specific to Python. So what really gonna happen is, if we heapify our array, this will restructure our array into something like this. This will perform some operations, and those operations are basically shift down. So what it's really going to do is it's going to push up the least values on the top and push down the bigger values on the bottom. So we'll go into that, but like just let's go through what really happened here. So the minimum value just came on the top. Minimum value is -4 in this entire array. That's right on the top, and it's on the 0th index, which is the root of our binary tree. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So now if you want to pop something, because that's the reason it's called heaps and min heap and priority queue. The reason is like you have given priority your minimum element, and it's sitting right on the top. All right. So because it's sitting right on the top and right in the front of your heap queue, if you want to access the minimum element in your queue, so what you will do is you will do a pop operation. You will do a heap pop operation. So just like here we did heap queue dot heapify, and then you provide your array right here. Same way for heap pop, you will be doing heap queue. By the way, first don't remember to import this. You have to import it, and then heap queue dot heap pop. So 2p, remember this, and then you provide your basically the array. So this will give you the minimum element, and this will pop this 4. So like, what if we really pop this 4? What happens if we pop it? So popping this will just take this away. It will pop the element, it will return it. Then we have just broken our binary tree. Like we have broken our heap. So what's really going to happen now? So what will happen is the minimum element. So what really happens behind the door is this element right here will take this position. This is how things work, and then again we'll perform a heapify, and in that heapify we will basically keep pushing this element to its right position, and so that like the minimum element gets on the top. So but let's say what really gonna happen now is we decide which value from these two will take place here. So from 1 and 0, this is the minimum, right? This is the minimum, so this minimum will go over here. Then this position is empty, so what will happen is out of 3 and 2, this position will be taken by 2. Now this 9 will basically come over here. All right, this 9 will come over here. Now again, this is converted to again min heap. Remember, initially when we just heapified it, it performed in big of n time, it performed heapify operation, which uses something called push down. So it's pushing down the bigger element to the bottom, and you can do same for the max heap. In max heap, what you really do is you negate your elements right here when you are heapifying it. Okay, so now how about heap push? Heap push meaning like you can push some element to your heap. So let's say if we heapify, same thing is going to happen. The same way we will be adding this to our heap. So heap q, heap push, so double p, and what do we want to push? So this is the array we want to push to, and second argument will be the element. So we want to put, let's say I want to push I would say like I want to push maybe 6. Let's push 6 into our min heap. So what's going to happen now is, since we are pushing 6, so we'll create basically a node, let's call it 6. Now initially what really happens is like you append this to basically the, you go to your left child, keep going to the rightest of your left child. So this is that position. What you're gonna do is you append it right here, but we're gonna figure out like if this is its right position. It's not. So what we do is we will bring this 9 over here and then take this 6 over here. This 9 takes its own place. Now is this 6 in the right position? Yes, it is. So I guess like that is its right position. Otherwise we will keep pushing it on the top wherever its right position is in comparing to its neighboring values. Then you can do a heap peak. Heap peak is basically you just want to peak the value on the top. So you can just take a peek of this, which is basically you can access this by min heap -1 value. Okay, so not -1, so I'm sorry, it's like the 0th. So you can do heap q dot heap peak, and it should return this value -4. Okay, well, -4 is not present here because we removed it while understanding things here, but you know what I mean. And then remember, I'm sure you remember this heap sort algorithm. That's where it comes from. What you really do is, once you have your heap right here, your heap right here, you keep popping the minimum element from your heap. So you have this, let's say this unsorted array in the beginning, you had that, you convert it to your heap. Now minimum element should be on the top. You pop that element and create your array. So 0. So maybe what I'm really trying to do is, heap sort works in a way like you converted your array into min heap, then you pop the first element, the 0 will come here. Now again, if you're removing 0 from here, this 1 will take this place. This 1 should take place of this 0. Now out of this 5 and 10, this should come over here. Now again, what do? You again gonna pop. So this 1, you again pop it out. So that's gonna be your second value. So 1 right here. Now out of 2 and 5, this 2 will take place on the top. So this 2 will come over here. This 2 will be right here. And then out of 6 and 3, this 3 should come over here. Out of 8 and 12, this 8 will come over here. Now you will again pop. So now I guess you understand what I'm trying to say. Then you will pop 2 again. So this 2 is out. This 2 is out, right? This 2 is out. You popped it. Now out of 3 and 5. So this is how you perform a heap sort. And because you are doing it for all the elements, and each time you basically pop and rebalance your tree, because you have just popped your one of the elements. Now it will take basically the height time, which could be worst case, it could be n if it's really unbalanced, and that's how you are going to have like a big of log n is the height, log n is the height, and this is basically you're doing it for all the element. That's why its time complexity is big of n into log n. Now we have understood heap, min heap, max heap, and you can do the same way. Max heap, you just need to negate all the values and then heapify it, then it will give you a max heap. All right, now let's see how it must have actually converted, it must have performed the heapify operation. So what really happened is, in the beginning we had this array, you know, this array. This is not like really, this is not the heap. This is this array what I'm talking about. This is the array. Let me copy this, and let's copy. Okay, and let's paste it right here. Okay, so this is the array that we are working with. This is the array right here. So this is not a heap right now, but let's convert it. Let's perform the heapify operation on it. How do we do it? Now, in order to heapify, it's going to have something called push down or push up based on its min heap or max heap. It will perform the very first operation. It will perform it. It's going to go to all its elements, and then especially, let's not go to leaves because it doesn't really need to decide over there, but let's go to first known leaf from the bottom, which is, let's say, this one right here. So this one here, it's in right position. This one you see right here, this is in right position. This 10 here, it's not in its right position because its child has to be greater than itself, because our root needs to be smaller. Alright, because it's a min heap. So we're gonna rearrange it like this. Then we come to 8. 8 is already done. -4 is already done. Then we're gonna come again here at our 5. So what will happen is we'll push 5 down. We'll take it out. So we'll take it out, and then this one should go up, take its place. This will come right here. Then in the next one, 0, -4, this negative should be going on the top. This should be going on the top right here. Now you go to the root, then you decide this 4, -4 should be on the top, and this 2 will come down here. But you're not done yet. You will keep performing this operation again and again until you are out of basically you cannot change your array anymore. So unless you can make the decision to change your structure, you will keep doing it until you have the minimum element on the top and its children also both smaller than itself, and then that basically satisfy for all these little cute binary trees you can see right here. So it should be satisfying this as well and this whole as well. All right, now we have done heaps and priority queues. Let's move on to the GOAT algorithm, which is Dijkstra algorithm. Now it's used for finding the shortest path from a source element or source node to all the nodes in our graph. So here I have drawn this graph that has basically 6 nodes from A to F. Now in green I have written the weight for traversing from one of the nodes to another. So you can see from in order to traverse from A to B, we're going to take our cost is 2, from B to D is 7, D to F is 1, and maybe in this case we can say like we have source and destination, but Dijkstra algorithm really gives you basically the shortest path from its source to all the nodes. So you should be at the end, once you finish your basically finding out the destination distance from your source, you should have all the distances from your shortest distance from your path from your source to all the nodes. So let's see how we are actually going to do it. Let's not perform our Dijkstra algorithm on the very this big graph, but like let's learn it from this small graph. So initially what really happens is we're gonna first let's figure out what are the distance from A, direct path from A to B. So we see a direct path from A to B, so the distance from A to itself would be 0, but distance from A to B is going to be, there is a direct path, so it will be 2, but there is no direct path from A to C, so this distance is going to be infinity. Okay, so this will be infinity. Now what we gonna do is relaxation. Relaxation is basically if there is the distance between from A to B, this distance, so A to B, which can be called I can call it maybe, you know, distance U. This node is U, and then we have this node V, So now if I'm saying that if the distance this has from our source, now this is 2, if 2 plus the cost of from U to V, what is the cost from U to V? 4. If 2 plus 4 is less than the distance of V, distance of V is this, infinity. So 2 plus 4 is less than infinity, which is 6 is less than infinity, then distance of V should be distance of U plus cost of this edge from U to B. So this infinity will be replaced by 6. Now we can understand how we have done this relaxation. Relaxation is basically realizing that you could travel from your source to, because you could travel to the node U from the source because there was a direct path. Now from here, or there might be not direct path, but you were able to get to B from somehow, and there is a distance you have, like you have traversed some distance, which is 2, you traverse the distance 2. Now if you can go to this next node, which is C, in less cost than its distance, so 2 plus 4 is less than its distance, then you can perform relaxation by assigning basically this short distance in comparison to the greater distance, which was infinity it had. So we're gonna perform the same thing in our bigger node, bigger graph. Okay, let's do that. So let's move it a little down so that we have a space to write things. So I guess you can see it. So we'll be performing this relaxation on all the nodes, except like if you see a direct path. So from A to B, I see a direct path. So it's gonna be basically I'm gonna take basically the distance from A to B is 2. So, and from A to C is going to be 4. Now the distance from A to D, I don't know, so I'm gonna have infinity. The distance from A to E, I don't know, so this will also be infinity, and distance from A to F, I don't know, so it will be also infinity. Now we're gonna perform relaxation on all these nodes. Remember, all these nodes we have basically pushed to our queue, and you will realize that like while doing these questions, how you implement Dijkstra is like you use this priority queue or min heap or max heap, whatever you guys want to call it. We just learned them, and you keep pushing all these elements to your heap, and because you are trying to find the shortest path, so this distance that you have, so basically right now this shortest distance to reach B is 2, so that will be the basis of your priority that you feed into your this priority queues or min heap. All right, so now what we're going to do is we're going to perform some relaxation from at node B, because it's in my queue. So I can basically draw a queue right here, or maybe, you know, like just have a queue like this. B is in my queue, then C is in my queue, then D is in my queue, and then E is in my queue, and then F is in my queue. So I'm just performing some relaxation on all these nodes. Okay, so I will take the node B, and then I'm going to perform the relaxation. So where can I go using B? So from B I can go to, there is a direct path from B to C, and there is a direct path from B to D. So let's check if this 2 plus 7 less than infinity. So this is the cost to reach B from our source to, and now there is a edge cost from, basically 2 was the distance, and there is a cost of 7 from going to B to D, and now 2 plus 7, 9 is less than infinity. So we will replace this infinity with 9. We will update this. We'll update this, then we gonna check in our queue. By the way, this is we are doing this with BFS. We are performing we are operating here with BFS because we are not like going in depth to just one branch and then keep going down until you can't go anywhere and then come back and then start traversing your another edge. Here you can see when we were doing, we just performed, we explored all the direct paths from A to all of its neighbors. Okay, so basically in DFS you keep going, you pick one neighbor, you keep exploring it until you have visited it fully or all its neighbors, and then come back and then explore your next neighbor. But in BFS you basically explore all the neighbors right together, like just all of it together. So right now we can see we are visiting B. So we have already visited A, now we are visiting B, and we have relaxed all its edges, and now we can basically pop it off from our queue. We'll pop it off from our queue. Now next element is C. Oh, by the way, we haven't relaxed this one here. So you can see the cost here is 4 from B to C, and if we basically relax from B to D, this path, so distance of from A to B is 2, so 2 plus this cost of this edge is 1, is less than the cost from A to C is 4. So now 3 is less than 4, so we will update this 4 with 3. Now we can delete this. Now is we can pop this B from this queue. We already popped it, but now let's take our next element and visit that. So we're gonna pop C. We are popping C, and let's explore this now. So from C there is a direct path from C to E. We have already explored this. So there is a direct path. So cost of coming to C is 3. That's the distance of U from our source. Now if 3 plus 3, this is the cost from going from C to E, so not E, 3 is less than infinity, so I will update this infinity with 6. Okay, I will update this infinity with 6. Then there is no neighbor of C, so I will pop this from my queue. And then I'm going to pick the next element, which is D. So I'll be visiting D now. So there is a direct path from D to F. Let's perform the relaxation. 9 plus 1. 9 was the distance. If you remember, 9 was the distance from coming from source, which is A. This is source to D. And we have calculated it after doing the relaxation at B. And we could reach to B from A, because there was a direct path. Now this 9 plus 1, which is 10, is less than infinity, so I will perform relaxation and update this distance with 10. Okay, now there is no direct path from D, so we have visited this. This visit is complete. We can pop this off. And then let's pop the next element in our queue, which is E. Now from E there are two direct paths, from E to D and E to F. Okay, so we're going to perform both relaxations here. So let's choose going from E to D. So distance to reach D from our source is 9, but if you see 6 plus 6 is the distance to reach here from A, so 6 plus, yes, you can see, so 6 plus 2 is less than 9, which is 8 is less than 9. So I'm gonna update this with 9, sorry, 8. Okay, so I'll update this with 8. Then this is done. Now let's go to our F. So 6 plus is 6 plus 5 less than 10. 11 is not less than 10, so we will not update F. So we have visited E. Let's remove this. Now we're gonna visit F. Let's visit F. But if you realize, there is no direct path from F to anywhere, and that too, this is my destination now. This is one of the most important algorithm, finding the single shortest path from the source node to your destination. This is the destination, and that we did using this relaxation technique, which we perform after we basically you put your source node into your priority queue, and then this priority queue basically keeps the most prioritized node on the top based on basically the shortest. In this case, it will be the shortest distance from this node to all its direct reachable neighbors. Okay, so this was it, and I think this will be really useful on all the problems that we gonna tackle. Graph is like really the big playlist, big series. So it's important that we cover this like early in the beginning, and we equipped with this knowledge to basically tackle all the problems that are going to come later. Okay, next, right before I wrap up this video, I just want to quickly cover BFS and DFS. We have already studied this in when we were doing binary trees or trees in general, but here we will be doing it more in terms of in the context of graph traversal. So I have drawn two graphs here, just the same graph, but one we will be traversing using BFS, which is breadth first search, and second we will be traversing using DFS, which is depth first search. Okay, so I'm just going to show the comparison right here. Breadth first uses basically data structure called queue. So we're going to have queue. Okay, so this queue basically keeps the node that we are going to visit in the order. So let's say this is my starting node, this is my start node. What I'll do is initially I will push that to my queue. So my queue initially will have A. Okay, now we'll have our while operation. While this queue is not empty, that means there are still some nodes that needs to be visited. So what I'll do is I'll pop this A, I'll pop this. So I will have right now I will have this A out with me, and this is the node that I'm visiting right now. So I will mark this visited. I'll have a visited set. Let's call it visit set, and it's gonna store all the nodes that we have visited. So right now we're visiting A. Let's mark this there. Now let's visit all its neighbors. So we're gonna visit B. We are visiting B, but remember, you're just visiting it, but before that, mark this to your queue because you need to still explore it. So queue is for exploring. For visit, you're just visiting all the neighbors. So right now I'm visiting B. I can visit B from A. So I'll append B to my queue and then F to my queue. But these two have been visited. Okay. So in my visited set, I have B and I have F. Okay, now I will pop from my queue because I need to explore more elements. I have not explored all the nodes of my graph, so I will pop. So right now I will pop B because that's in the front of my queue. So right now I'm exploring B. So while exploring B, I'm going to reach out to its neighbors and I'm going to visit all of them. So I'll add it to my visit set. So C, E, and D. So these are in my visited set now. Now while I was visiting them, I'm going to append them to my queue in the same order that I visited. So it was C, E, and D. But remember, now my queue has like 4 more elements that need to be visited. So now B, I have explored all the elements of B. So this B is done exploring, A is done exploring. I will basically get rid of B. Now I'm gonna pop the next element from the front of my queue, which is F. So F is out. So explore F. So in order to explore F, I'm gonna check like what are its neighbors that needs to be visited. By the way, these are all visited right now. So now this doesn't have, this D is already in my visit set, so I don't need to visit this. So I'll just basically get done with F, pop out next element, which is C. Let's pop it out from the queue. So C is what we need to explore now. C doesn't have any neighbors, so this is done. Let's pop out the next element. We're popping out E. E doesn't also have any neighbors, and then we're gonna pop out D. So we have explored everything and we have added every visited node into my visit set. That's how you visit and you explore. Okay, so now since I have also explored D, now my queue will be empty and I have explored all the elements. Okay, that's how you do it in BFS. And I know I'm rushing through things, but that's how you do it. I guess, like, let's write down the little algorithm that we just performed. So while queue, we're gonna pop the node queue.pop. That's how we're popping. So node is what we're gonna add it to visit. So visit set.add node. Or you can do it like inside the for loop. So for all the neighbors in node, we're gonna append those to your queue. Queue.append. So that's how we do it. We're just quickly wrapping it up. Okay, we have done this in, it's the same way that we do it in graph also, the same way you do it in binary trees or trees. So let's do DFS now. DFS. So how do you do DFS? This is called depth first search. So you use the data structure stack. So we'll be using a stack. What do you do in the stack? Let's say this is my start. A is my start right here as well. Start is right here. So I'm gonna what I'll do is, like, I will take A and I will basically, right now I'm exploring A, so that will go onto my stack. So that's the first node that I'm visiting. So let's have visit set right here. So you will know, like, the order will be different when you do BFS versus DFS. So what I'll do is, like, I'll pick one node, we'll pick one neighbor of it. So I'll pick the neighbor B. So right now I had A, but then I'm gonna pick the neighbor B. So I'm visiting A right now. So I'm visiting. I'm not done visiting. I'm visiting it. But then while visiting it, I'm gonna explore its neighbors. So I'm gonna explore B right now. So my bad, like, I shouldn't have drawn this. So I'm just gonna pick one neighbor. So I'm gonna visit B, but I'm gonna explore B now. So I'm gonna pick its one neighbor, C. So I'm gonna explore C now. So once I visit, then only immediately I start exploring its all the neighbors of that visiting node. I don't put it in the priority queue for just let's explore it later. No, I immediately start exploring. So what I'll do, I will explore C as well. And right now while we are visiting, we can keep adding it to our visit set. It doesn't really matter. Okay, so A, B, C, these are all visited. We can start adding to my visit set. Now I will I'm done exploring C. There are no neighbors to C, so I'll pop it from my stack. I will pop it from my stack. So what I'll do, I still have B, and do I have other unvisited neighbors of B? Yes, I do. I have E, so I'm gonna explore E. So I'm visiting E. But I'm also gonna explore E. So let's add it to my visit set. E, let's explore it. It has one neighbor, which is D. So I'm gonna visit D and append it to my stack, and then I'm gonna start exploring D. So while I'm exploring D, so what I'll do is I'm gonna reach out to its unvisited neighbors. So this B is already in my visit set, so I'm not gonna put that onto the stack because this is already being visited. It's right here, you can see. So I'm not gonna do this. I'm not doing that, although it's gonna stay connected. But then I have one more neighbor, which is F is connected to it. There's just one neighbor. So what I'll do is I'm gonna visit that. So I'll be visiting it. So I visited D, and then I visited F. Now I will put that on top of my stack F. Now let's explore F. Does F has any unvisited neighbors? No, it doesn't. So I'm gonna pop that from my stack. Now does D have any unvisited neighbors? Unexplored, no, not right there. So although we cannot choose this because this is already visited. So we have gone from here, this is all covered, and I think this is also covered. So I will pop D because it doesn't have any unvisited neighbors to explore. Then E also doesn't have anything, so we're gonna pop this off. Then we're gonna come back to B. So we're gonna pop this off because also it doesn't have any name, and then we're gonna come out of this stack. So now our stack is empty. We have explored all the neighbors. So that's how you do it. And if you remember, this is how we visited. So we visited A, then we went to B, then we went to C, we came back, we went to E, from E we went to D, from D we went to F, from F we came back to E, we went back here. Since this edge is not covered, but all the nodes are covered, this was unnecessary edge, or it was unused edge, I could say. And then we come back to A. So we just explored the entire graph and came back. All right, so that was the wrap up of all these little concepts that we needed to go through before we dive into further more complicated graph problems. Okay, so that is it. I'll see you guys in the next problem, which is minimum effort path, or whatever it was. I think it was let me go back. Let me switch. Yes, path with minimum efforts. That's the problem we will be doing. I don't want to. This video is already too long, so I'm gonna have the problem done in a separate video.